It's a pleasure to welcome you today. Let me introduce myself and my colleague. My name is Mikhail Gorelov. I am the head of IT support division in Sberbank. I'm here in my function as project manager of a new Sberbank IT platform transformation program. This is my colleague Vladimir Komarov. He's an IT architect in Sberbank. So the topic of our presentation is the high availability and fault tolerance of a grid. I think this information will be interesting to those who are planning to build solutions based on in-memory grids and at the same time ensure a higher level of availability. So we would like to share our experience with you, the challenges we have faced, as well as expectations we have about the new system. Our presentation is actually divided into two parts. First of all, I will briefly tell you about the issues and requirements we are going to address with the new system. So I think there will be time for questions at the end of presentation, and in any case we will be open to questions after the presentation as well. So let me start by telling you a few words about Sberbank. Sberbank is the largest bank in Russia, so there is more than 60,000 offices in Russia, more than 110 million retail clients, 50 million active users of web and mobile banks. So according to the IT roadmap, Sberbank is now working on the realization of a strategic program which is meant to transform core banking systems. We have called it Program 18+. One of the main goals of the program is to migrate from high-end hardware, from high-end servers and high-end storages to the x86 servers. So, and commodity hardware will be the foundation and the main environment for the platform, which in its turn and will be based on the in-memory data grid. Our target topology is about 2,000 servers in production environment. And it's clear to us that within the course of a program we are faced a huge number of solution reliability issues, and especially considering the consequence of possible data loss, which is totally unacceptable for any bank. So, so imagine that you have something about 40 critical systems with a current level of availability of almost all services of 490. So, and your task is to achieve the same 490 availability rate on the new platform. So, sounds hard, doesn't it? By the way, this is only one of the large number of tasks we are addressing while developing the new platform. I'm not going to mention it because it could be a topic of another presentation actually. For now we are suggesting to focus in on issues which is how to achieve the maximum reliability of IMDG based on a bunch of x86 servers and at the same time distributed through the 2 geo distributed cluster. So what would you begin with? Obviously what we did is that we assembled a large team of developers and support guys. After that we defined our requirements, discussed those requirements with our business team, described the basic scenarios of methods of testing and cases. So we recorded indicators of system availability and recovery. And I would like to draw your attention that at the initial stages we had got support guys involved in the project and made them a part of a project team. Okay, let's move on. So the support team and the architects made a big picture of key mechanism in accordance with our priorities. And when we started the stage of development and implementation, we also defined some methods which would help us to measure the current level of reliability. So what are these methods? First of all, additional tools for control. For example, we have developed some tools for checking local file store, snapshots, checking cluster topology, and others. Sorry. Monitoring improvement, continuous testing. Speaking of stress testing, we have built separate landscape for testing, and size of this testing area is actually just the same, is exactly the same as production environment, production landscape. So I mean the number of servers and all of the hardware is the same. So and we actually have more than 45 testing cases, and we do them weekly. As a result, each time we ask ourselves, do these results suit us? Does grid operate correctly? For example, does response time, recovery time, rebalancing time suit us, even in case of failure some nodes? What can we do to improve the result? And how does the number of nodes affect the performance and manageability of a system? So keeping incident response plan. Several business tasks, for example, a customer profile, P2P transfers between the customers, are actually working on the in-memory data grid today. So they're working in a pilot mode, serving a limited number of customers, or for example bank employees, but anyway the number of business cases is increasing, and for this reason we have already implemented our current incident system, management system, for building the same process around the new platform. So it's necessary, if it is necessary, we will update our disaster plan, release the new patches or fixes. Now let's take a look at this slide. So I would like to say a few words about important threats. We have focused on this group and we have defined the functionality inside the platform, inside the grid gain, which will prevent the major threats. As I described earlier, 100% of no data loss is extremely important for us. And this is the most important requirement from our business. So one of the key mechanisms for reliable data storage is on-disk data persistence. Grid gain software actually has functionality for storing files on disks. This is a LFS, local file store. By the way, in most incidents which required platform reboot, by default, we have successfully recovered our data from LFS, from local file store. Needless to say that data must be stored in several copies. We have determined for ourselves an essential and sufficient number of copies. So it's a fourfold backup. 2 copies allocated in the first data center and 2 copies in another. And this is how the data are actually distributed in our system today. So distributed cluster. We want to protect ourselves from the local data center disasters. So we have built a distributed grid. As I previously said, our target is about 2,000 servers in production environment. They will be distributed between 2 sites in Moscow, and the distance between them 30 kilometers, something about it. So data snapshots. You will be interested to know that we have had to recover 2 times from the snapshot since the first day of using this functionality in our pilot mode of production environment, and it was really successful recovery. Yeah. So frankly speaking, I have to say that we are still finding bugs in this functionality and correcting them together with grid gain. However, we believe that considering a 4-fold backup, local file store, geo-cluster, so considering on that, we think that additional backup is necessary. Yes, we are paranoid on this point because we have bank. So in addition to snapshot functionality, we consider that it's important to realize the possibility to restore from snapshots not only at the moment of their creation, point-in-time recovery, not on the point of their creation, but also at any point in time. For example, at the point of incident or at the point before it, before the system is down. In our opinion, the integration of write-ahead log and data snapshots plays an important role in developing point-in-time functionality correctly. Volodya Komarov will give you more details about it during his part of presentation. Moving on, so health self check. As I said before, that our team include both developers and support guys, support team. And you know, when we were discussing cluster size, about 2,000 or actually several hundreds of servers, the guys from support said, hey, we want a built-in mechanism for detecting issues and errors inside the grid. In other words, we would like to see the system which can analyze its health on its own and send us an issue notifications. And that was one of the important requirements from our support team. Speaking of reliability, data replication, did I say that we are obsessed about reliability issues? Yeah. So we think that one of the priorities is the creation of a mechanism for asynchronized and synchronized replication between different installations of a platform between different grids. And our business case also includes the usage of separate installation as additional data protection and data archive. So it seems that I reached the end of my part of presentation. I have given you a brief introduction and highlighted the challenges we are facing. So I'm going to turn it over to Vladimir. Volodya, please.
Thank you, Mikhail.
Thank you.
So Mikhail says we are implementing the new core banking systems. As you know, the legacy way to implement grid-enabled application is to use a grid as a cache. Someone may say it's easier. Yes, it's true, but it's true only if you obey some rules. First, you have to use object relational mapper instead of direct updates through JDBC. And second, you cannot update the data passing of the application. It sounds very easy, but indeed restriction is quite strict. Yes, we could build our application like this, but there is still one severe issue. We have to use high-end hardware to implement database system. Even the most powerful server can't serve all the Sberbank activity. That's why right now we have to support several core banking systems. They are product aligned, and this approach doesn't give us time to market and flexibility. That's why we decided to completely rebuild our system. Our architecture looks like this. The grid is the last frontier, so there is no database underneath the grid. Grid has to provide data persistence by itself. We have tested a lot of distributed in-memory data platforms, including the solutions from known IT leaders, IT market leaders, and finally we have chosen GridGain as the most powerful and reliable platform. But of course, we are still implementing the new features and fixing new bugs, but we face the future with optimism. So before we start protecting something, we have to list and categorize the threats. Now you can see the tree of business continuity threats. Indeed, it's better to use hypercube instead of tree, but it's very difficult to draw the cube, and it's much more difficult to think of the cube. Indeed, the third dimension is the reason of a failure. So we can distinguish three possible reasons of a failure. First is application software issues, the second is user and administrator actions, and the third is system issues. Now I'll focus just on system issues. So speaking system, I mean hardware, system software including operating system and Java machine, and the platform software, it's GridGain itself. So let me briefly explain how do we change the behavior of GridGain. The GridGain provides ability to write kind of plugins to the grid. So this ability is called SPI, System Provider Interface. Now I'll tell about two SPIs. They are Affinity function and topology validator. So what is Affinity? The data is distributed across nodes in three steps. First, node filter selects a set of nodes for concrete cache. Second, the records are divided into partitions, or maybe chunks or shards, but in GridGain terminology, the indivisible part of records is called partition. And the third step distributes a partition across selected nodes. So we decided to change the default distribution rules, and GridGain provides Affinity function SPI to change this. So let me introduce the concept of data cell. We decided to limit data linkage with some nodes. Let me explain why. First, if a node fails, another nodes should take over the slot and perform data rebalancing, redistribution. So the more nodes in the cluster, the faster is the recovery. On the other hand, the common hardware is quite reliable, and the fully broken node is not so often. More often we can see semi-broken node. Let's say network interface was broken, or maybe part of memory was broken, or maybe the performance just decreases due to memory leaks, and the semi-broken node affects the performance of all the linked nodes. So the more linked nodes, the stronger is performance impact. So we have to find kind of balance between large cell and small cell. Our tests show that quite optimal amount of nodes in a cell is 8. So in the right part of the slide you can see the example of a cell. So the cell consists of 8 nodes. Every node resides on its own physical server. So every partition and every record has 4 copies, 1 primary copy and 3 backup copies. As you can see, both data centers are active, so the workload is distributed across 2 data centers. So the second reason to make cells is not so obvious, but it's very important. Sometimes we have to update software, and we have to put some nodes out of the operation. But it's impossible to stop the grid as a whole. So let's imagine you are paying, let's say, in restaurant by a card, and processing system is stopped. You can't pay. It's unacceptable. That's why we have to perform rolling upgrade. But when we put a node out of operation, we have to be sure that all the data still remains in the cluster. So if we see a cell, we can safely switch off up to 2 nodes from a cell. One node from data center 1 and the second node from the data center 2. That's why all the cluster nodes could be updated in just 4 steps. So let's take a brief look at Sberbank infrastructure. As you know, the best shield is the shield protected by another shield. So the server and network hardware must be as reliable as possible. As you see, every server of a cell resides in separate rack. So this distribution is achieved by our proprietary console that performs grid node start. The second, the network is built using closed topology. So if a network switch fails, the network integrity is not lost. And the third, data center interconnect is physically doubled. So even a crazy excavator can't break it. But despite the complex network architecture, we have to be ready to meet cluster fragmentation. You can see different types of fragmentation. So the common case is just a node loss, but sometimes we face fragmentation, and we have to be ready to recover a cluster. So let's consider the recovery process. It's a recovery process provided by grid gain. First, the grid has to finish all the active transactions. So transaction can be committed or rolled back. It depends on the transaction state. Second, the grid has a special node called coordinator. So if coordinator leaves, the new grid has to select new coordinator nodes. And the third, grid calls topology validator validate method to check if the new topology is valid. So by default, every topology is valid. Default implementation of topology validator is just return true. If topology became valid, grid continues normal operation, and if topology became invalid, grid goes to read-only mode. But read-only mode is acceptable for, let's say, web application, but it's unacceptable for banking platform. So that's why we are in negotiation with GridGain to add so-called admin wait mode. It's a mode when a grid cannot accept neither read nor write requests, and it is waiting until the admin says go on. So let's explain our vision of cluster validity. First, we have to check simple cases. If the previous topology is valid, and if the node a node was just added, or maybe we lose several nodes, it's okay. We can continue normal operation immediately. But if we meet complex case, we check several variables. First, we have to count how many nodes left in each data center 1 and data center 2. And second, we have to check if there was no partition loss. When we calculate these variables, we check the set across the table. The table is quite compact because there is some impossible variable combinations. So let's say if all the nodes from data center 1 are in place, there is no data loss. But there is one more issue. In case of cluster fragmentation, a new cluster doesn't know anything about another cluster. So if a cluster is valid, it can return to normal operation, but it doesn't know if it's the only cluster that returns to normal operation. So if two clusters returns to normal operation, we get kind of schizophrenia named split brain. So there are several approaches to avoid split brain. The first approach is data center priority. So if a new cluster resides in, let's say, data center 1, it continues operation despite of what happens to another nodes. But the most robust approach is to use the additional cluster component named quorum device. The quorum device is an extra server resided in a special data center with a dedicated interconnect. So as you can see in the slide, every cluster reports its state to the quorum device, and the quorum device can confirm or reject the cluster decision. So the advantage of this approach is that quorum device never confirms two positive decisions. So it guarantees that only one cluster continues a normal operation. Let me remember again that our cluster resides in two data centers, and the quorum device resides in special third data centers with dedicated interconnect. So even if a data center interconnect breaks, there is still ability to access quorum node and report the new cluster state. The last but not the least topic is local file store. As you know, the early versions of GridGain came with cache store SPI, so you could use your own persistence solution. But now GridGain has implemented LFS, it's a local file store. As you can see, every node is now kind of a local database. Its architecture is quite close to traditional disk-based database such as Oracle and maybe Microsoft SQL. All the data changes are written synchronously to the write-ahead log and to memory. And then the asynchronous process writes the memory blocks to storage file. So that's why GridGain guys say now about memory-centric application instead of in-memory application. So the extra value of LFS is that now we are not limited by RAM size, we are limited just by storage size. And as you know, even the flash storage is much cheaper than RAM. Of course, we have to carefully test all the mechanism. We have to add new mechanisms. We have to implement some additional tools before we can start the GridGain as a fully functional backend for core banking system. But we face the future with optimism because we are in cooperation with best architects and developers from GridGain and Sberbank Technology. So that's all. Thank you for your attention. If you had any question, me and Mikhail, we are glad to answer. So the grid restarts very quickly because there is no need to read all the data into memory. Grid performs lazy read. So at the time of restart is equal to time of starting GVM and application. So the grid is ready immediately after starting.
Which
we are currently run GridGain Ultimate Edition. The version number is, as far as I remember, 8.1.3.
So this is not open source.
Okay, so there is no way to translate it to Ignite version, which is a version 2. Something.
I think this is something different between the versions. And as you understood, as you know, open source version Ignite doesn't have any additional things like the snapshots.
So traditionally, enterprise-grade components are part of a commercial version. It doesn't go open source. Yes, please.
Quick question. So during real VR instance, right, you don't really have time to do the what you're doing in the weekly exercise. Break it down nicely, make sure data are completely synced over, replicated. So what is SLA that's trying to hit? Like
sorry, if, as far as I understand, you ask about data loss SLA.
Yeah.
RPO recovery point is strictly 0. We cannot lose any transaction. And RTO is, so it's better Mike to answer this question.
Our goal is, if we're using only in-memory grid, we think that the maximum RTO could be something about 15 minutes.
15 minutes.
Yeah.
I see.
So, and no data loss is extremely important. So RPO is 0.
But in a real DR situation, right, there certainly have to be some data loss, minimum, obviously, right?
Yeah.
Because your replication is going forward to the other asynchronously. You have no time to bring that replication up to the tip before things really go down roughly, right?
Right.
Yes.
What will happen if quorum nodes fail?
If quorum node fails, cluster will wait until it goes up. But even cluster is in no operation mode, admin can manually bring it up.
So how do you monitor so many nodes, health of so many nodes and metrics?
It's a good question. We are working on monitoring architecture. So the currently accepted approach is to use GMX metrics on each node, and then we are planning to use to aggregate these metrics with grid gain web console, and then transmit the metrics to our monitoring system. If you're interested about the name of monitoring system, it's Splunk.
Not exactly. Actually, at this moment, we're using the current monitoring system for our hardware environment. This is actually HP tools, HP monitoring system, and for grid gain monitoring, we are going to use Zabbix, and it will be something like Umbrella. It will be Splunk. So this is how we think it works.
With a huge size of the clusters here, what's a typical time it requires to find that the topology is broken, and when the topology gets revealed in a separated cluster, what time was it? I'm asking because the case situation by using some load balancer, my next request as a bank client would be directed to already separated portions of the data center. And in this case, of course, the records would be corrupted. So, what about losing or corrupting, risk of corrupting data at that time?
It's an issue because now it takes quite a long time to understand that the topology is corrupted. Let me turn to this slide. As you can see in upper left picture, it's so the topology ring crosses data center border only twice. Indeed, it's not always possible, and a ring can cross topology border more than 2 times. It's let's say maybe 10 or 20 times. That's why heartbeat is quite slow, but we are working on it, and it's a severe issue, and we plan to reduce the heartbeat time.
Check out iCube 800.4, which calls token bus architecture. They have a very fast recovery of data. To recover tokens and topology.
Okay, thank you. Let's discuss it a bit later. Thank you.
Thank you, Alexander.
So you have 2 effective data centers, and do you replicate data between them, or you just use 2 lines?
Actually, it's this is an active cluster, and the data is distributed between two sites. This is not different. This is no difference between these sites. It's one grid distributed on one circle between two data centers. Yes.
So just look at the picture with the cell. You can see every cell is located in two data centers, and every cell has active partition in both data centers. So it's a single united grid.
Yeah, and we think that it's important to develop a new functionality like synchronize replication between different circles, between different installations of the grid. It will be the real replication. So.
So if every cell has 8 nodes, so we have multiple of such cells, nodes.
We are not Google. We have just two data centers.
You said you have 2,000 nodes, correct?
Sorry.
You have 2,000 nodes, correct?
Now we have, let's say, 134 nodes in production, but we are planning to increase the number of nodes. And,
Okay, so 136 nodes. So every cell has 8 nodes, right? That means there's multiple cells in each data centers.
So the cell is just a logical concept. So the grid is still united, but the data linkage is reduced to 8 nodes. But the heartbeat is not reduced by 8 nodes. So the grid still consists of more than several hundred nodes.
You guys mentioned you guys override topology validation. So how do you guys check for if the partition has all the data when you go to replace? You guys mentioned a couple of slides back. Yeah, right here. So you mentioned that you guys check to see if a partition has all the data. Like, how do you guys check that?
This is a grid gain API. We just call the grid gain method. It's not our know-how. You can even download Ignite source code. It's not enterprise functionality. Okay, I think it's all. Thank you very much for your attention.